In today's lesson, we're going to talk a little bit about degree of freedom analysis. And you all already know how to do degree of freedom analysis, even if you don't really know it by that name. Degree of freedom analysis is basically a method for deciding whether we can get a unique solution to a problem. So for example, if I gave you the equation x plus 3 equals 5, you would say, yes, I can find a unique solution to this question because I have one unknown, which is x, and one equation, therefore I can solve it, and the unique solution would be x equals 2. Right? One unknown minus one equation. If I said to you, though, x plus y equals 5, then you'd say, well, I can't find a unique solution to this problem because I have two unknowns and one equation. So this is basically a degree of freedom analysis. If the number of unknowns minus the number of equations equals 0, you can get a unique solution to the problem. If it equals more than 0, in this case 1, there's no unique solution. Now there's a little caveat to this, which says that the equations here that we're subtracting need to be independent equations. So let's just recap what an independent equation and a dependent equation are. So if I have, for example, this equation x plus y equals 5, and I gave you the equation 2x plus 3y equals 11. These two are independent equations because there is no mathematical operation that I could do to get from this equation to this equation. So if I tried to get the 2x and multiply by 2, I'd have 2y and 10, not 3y and 11, right? And you can try out different things. But if I told you 2x plus 2y equals 10 is your second equation, then these two are dependent equations. Why? Because if I divide this by 2, I'm simply going to get x plus y equals 5. And again, I wouldn't have any unique solution to this question. So what we're doing when we're doing a degree of freedom analysis is basically we're saying the degree of freedom equals the number of unknowns minus the number of independent equations, and that's a general degree of freedom analysis. Now when you do systems in mass and energy balances, sometimes you're going to also have other equations that are given to you. So whatever other equations you get in the problem will also be included in this degree of freedom analysis. So now let's go on and do an example of a very simple one-unit system and see how we can apply a degree of freedom analysis. Okay, let's do a simple example of a degree of freedom analysis on a one-unit system, and then we'll give a couple of different cases to see how it can get a little bit more complicated. So first of all, we have a unit that's a separator. It's separating component A from component B. So we have a feed flow that has 1,000 kilograms per hour, where half of it by mass is component A and half of it by mass is component B. And it separates it into two product streams. The top product we'll call M1, and it's composed of pure A. And then product stream 2 is M2, and this one has only 10% of A and 90% of B. So we've got a little bit of a separation going on here. Now, when we're doing a degree of freedom analysis, first we have to decide what our system is. So our system is, we're gonna go and circle our system. So it's just a separator because that's our entire system here. And then we look at the flows that are going into the system and the flows that are going out of the system. So here, obviously going in, we have the feed. Going out, we have M1 and M2. Now, how many unknowns do we have in these streams? So we just go ahead and count them. We look at the feed stream, no unknowns. We look at the top stream, M1 is an unknown. And then we look at the bottom stream, M2 is an unknown. So we have two unknowns in this system. Now, to find the number of independent equations there's a really simple rule. When you don't have a reaction, so when you have a non-reactive process, the number of independent equations you're gonna have is going to equal the number of species that you have. So in this case, we have two species. We have species A and species B that we can do a mass balance on. So we have two unknowns. We have two species, A and B. So two equations, meaning we have 0 degrees of freedom, and we can get a unique solution to this problem. And I'll do an example of that in another video, something similar to this where you can actually see how to go through the solution. But how come we only have two equations? We can do a mass balance on A. So A goes in equals A goes out in each one of these streams. We can do a mass balance on B. So B goes in equals B goes out. There's none in here and there is some in this stream, right? And then we can do a total balance on everything that goes in must come out. However, we discussed earlier about dependent and independent balances, and the total balance is going to be dependent on the other two balances. So basically, if you add the balance of A plus the balance of B, you'll get the total balance. And that's why the number of independent equations is only equal the number of species in a non-reactive system. So that's the first example. Now let's make it a little bit more complicated. What if I erase these and instead of telling you what weight percentage you had of A and B in the bottom stream, I said the weight fraction of A was X and the weight fraction of B therefore is 1 minus X. So in this case, if we count the unknowns, now we'll start all over again. I'll erase this. So now when we look at our unknowns in the system, we have M1, M2, and X. So we have 3 unknowns. And again, we only have 2 species, right? We have A and B. So 2 equations, 1 degree of freedom, and you'll find that you won't be able to solve this problem, right? It's underspecified. But now, what if I went ahead and gave you another equation, right? We said that the degrees of freedom is the number of unknowns minus the number of independent equations minus any other equations. So the independent equations are the species balance for A and B. But what if I told you that M1 is 3 times M2? Then now you would have this additional equation which will give you a connection between these two. So we have, relation M1 to M2. So that's going to be another equation. And in that case, you'll be able to solve the problem. Now, you'll find as you go through these problems that you're given a problem description, and you yourself are the one writing the names of the unknowns. So what if I had done something silly, like writing X and Y here? In that case, it would look like I had 4 unknowns instead of 3 unknowns, and this would still be unsolvable. But then you have to remember that you have this additional equation which is always there, which is that the sum of all the mass fractions has to equal 1. So another kind of implicit equation here is X plus Y equals 1. That would be an additional equation that would let you solve it, but you can simplify things for yourself, and rather than writing X and Y here, you would write X and 1 minus X. So that's basically the simple explanation of degrees of freedom. And you can see that it's something that you kind of have already known in the past just from solving systems of equations, but here just gets a fancy name and you apply it to processes with mass and energy balances. Hey guys, hope you enjoyed this video. If you did, please subscribe and turn on notifications for the next videos. If you have any questions, leave them in the comments and I'll do my best to answer them. And I'll see you all in the next video.